Hi everybody, welcome to our video on initial value problems. This is our fourth video in our integration series. An initial value problem involves finding a function y when we know its derivative dy dx and its output value y naught for a particular input value x naught. Initial value problems are important in mathematical modeling in a range of different fields. In this video, we're going to learn about initial value problems, and we'll find solutions to some example problems. And we'll find those solutions using integration. So, to start off with a first example, we want to find the function y when the derivative dy dx is equal to 2x. And we also have some initial information that y is going to be equal to 4 when x is equal to 2. So in mathematical terms, what we have here is we have a differential equation, which is the derivative dy dx is equal to 2x. And we also have an initial condition. So when our x value is equal to 2, our y value is going to be equal to 4. And that's written here mathematically as y parenthesis 2 is equal to 4. So to solve our initial value problem, we first solve the differential equation dy dx is equal to 2x. And the way that we do that is we integrate both sides with respect to x. So on our next line here, we have the indefinite integral of dy dx with respect to x is equal to the indefinite integral of 2x with respect to x. So if you remember that differentiation and integration, they're inverses of each other. So if we start with a function y and we differentiate it, we get dy dx. Likewise, if we started with a derivative dy dx and we integrated it with respect to x, we go back to the function y. So on the left hand side of the equal sign here, our indefinite integral of dy dx with respect to x, that's y plus a constant of integration c1. Then after the equal sign, we've got the indefinite integral of 2x with respect to x, and that evaluates to the antiderivative x squared plus another constant of integration c2. So if you followed some of our earlier videos, you've seen that when you take an arbitrary constant and then you add or subtract another arbitrary constant, that results in simply another arbitrary constant. So what we can do is we can combine the c1 and the c2 into a single constant c. So that gives us our next line, that our solution of our differential equation is y is equal to x squared plus c, the constant of integration. So this is the general solution of the differential equation dy dx is equal to f of x. It gives all the solutions of the equation for each value of c. So what we do next is we now evaluate c to find a particular solution that solves our initial value problem. So to find the particular solution, we evaluate c using the initial condition. Our general solution for our differential equation was y is equal to x squared plus c. And we have the initial condition that when x is equal to 2, our value y is going to be equal to 4. That's written here as y parenthesis 2 is equal to 4. So what we do now is we take that information from the initial condition and we substitute it into our general solution to our differential equation. So instead of y, we've got 4. Instead of x, we've got 2. So our general solution becomes 4 is equal to 2 squared plus c. So that evaluates out to 4 is equal to 4 plus c. And then our 4's cancel on either side of the equal sign. And that gives us our constant of integration c, that's equal to 0. So we can now substitute c equals 0 into our general solution y equals x squared plus c, giving us our particular solution to our initial value problem, which gives us y is equal to x squared. So we've done it. We found the function from initially being given a derivative and an initial condition, an output value for y for a given input value for x. What we're going to do now is we're going to see another initial value problem based on a specific real-world scenario. So here in our second example, we've got a decelerating car. A car is traveling at 10 meters per second. The driver applies the brakes and the car decelerates at a rate of -1 meters per second squared. So we want to know what velocity will the car have after 5 seconds of deceleration. So looking at this information, what we have here is we have a differential equation. Our acceleration dv dt, which is the change in velocity per unit time, that dv dt, that's equal to -1 meters per second squared from our question definition. And we also have an initial condition. Our velocity at time 0, so our start time, that's written here as v parenthesis 0, that's equal to 10 meters per second. So this is the information that we're going to start with while we attempt to solve our initial value problem. So to find a solution, we first solve the differential equation. So we have the derivative dv dt, the change in velocity per change in time, that's equal to -1. So to find a general solution, we integrate both sides with respect to t. So we've got the indefinite integral of dv dt with respect to t is going to be equal to the indefinite integral of -1 with respect to t. Similar to previously, our term on the left hand side of the equal sign, that evaluates out to v plus a constant of integration c1. And our term on the right hand side of the equal sign, that evaluates out to -1t plus another constant of integration c2. So similar to previous, we can combine our constants of integration into a single constant, giving us v is equal to -1t plus c. So this is the general solution of the differential equation dv dt is equal to a function f of t. It gives all the solutions of the equation for each value of c, constant of integration. So we now evaluate c to find a particular solution that solves our initial value problem. And to find the particular solution, we evaluate c using the initial condition. So our general solution to our differential equation, we just found that that's v is equal to -1t plus c. And we have the initial condition that at time 0, our velocity v, that's equal to 10. So that's written here as v parenthesis 0 equals 10. So what we do, like before, is we substitute in our initial condition values into our general solution. So instead of v, we've got 10, and instead of t, we're going to have 0. So our general solution equation, v equals minus 1t plus c, that becomes 10 is equal to minus 1t plus c. And we substitute in 0 for t, we get 10 is equal to minus 1 multiplied by 0 plus c. And when we multiply that out, we get that c is equal to 10. So now we substitute that c is equal to 10 into our general solution. V equals minus 1t plus c. And that gives us our particular solution to our initial value problem. So our particular solution is that our velocity v is equal to minus 1t plus 10, where t is equal to time. So with our particular solution to our initial value problem, we can now find the velocity of the car after 5 seconds of deceleration. Our particular solution is our velocity v is equal to minus 1t plus 10, where t is equal to time. We substitute in our value of 5 seconds for time, and we get v is equal to minus 1 multiplied by 5 plus 10. And that evaluates out to our velocity is equal to 5 meters per second. So we've found our solution to our initial value problem, and we've used that solution to answer our question. So in this video, we've learned about initial value problems. Initial value problems are important in mathematical modeling in a range of different fields. You will see them come up, and as you learn more about calculus and you work through further material, you do see them come up repeatedly. I hope that you found this video useful. See you next video.